Hi, today we will find the electric potential inside and outside a spherical shell. This spherical shell carries a charge distributed uniformly on its surface. This means that there is no charge inside this sphere. The charges are only on this thin surface of this sphere. Okay, we see in this figure I draw a sphere that has some radius. Let's say that this radius is r. We proved before that inside this spherical shell we have no electric field. We have this video that I added in the description where I am proving that we have no electrical field inside the spherical shell, and outside the spherical shell we have an electric field, and it's radial, and it's measured by this equation, where r is the radius of the sphere and q is the total charge on the sphere. And we have a video where we proved this formula. You can see in the description too. And in order to calculate the potential, let's recall that the potential is the line integral for the electric field. Let me write this. In order to find the potential at a point exists at r, which r is an arbitrary position of this point, we will take the line integral for the electric field between r and infinity, where infinity is the selected reference, where the potential is 0. Okay, now we will apply this formula upon our case. Firstly, we will start by finding the electric potential outside the shell, and then finding the electric potential inside this shell. Now we will find the electric potential at some point r. I will locate the point outside the shell, and as we said, it has the position of r. Now let's complete writing the equation. We said that the electric field outside the shell is calculated using this equation. We will assign the right hand side of this equation to this equation, and regarding to the path, this path will start at r, namely this point, until infinity. Okay, let's say infinity is there, so this is the path. And as we see, this path is aligned with the radius of this sphere. Okay, this path is radial, so this differential path is dr. Now let's plug the right hand sides of these equations, this and this, in this equation. And before writing, let me add something. If we said that this is a vector, okay, as we see, this path is radial, so the unit vector accompanied with this is ar. Due to this, the dot product between this and this is going to eliminate the unit vector, so I'm not going to write them down below. And as we see, all parameters inside this integration except for r squared are constants, so I'm going to take them out of the integration. Now we know that the integration of r squared is minus 1 over r, and then after taking the integration, I'm going to substitute these two limits of the integration. And now as we see, this is the electric potential. This equation is the electric potential outside the spherical shell. Now let's find the electric potential inside the shell. I draw a new shell, and I'm going to apply the same formula. The potential is the line integral of the electric field. Now I will draw a point inside this shell. Let's say that this point has an arbitrary location of r. Let me draw it down there. I prefer this. This is our point. Now, as we see, we are going to take the line integration between r and infinity. Okay, this until infinity. Okay, now we see that the problem is in this path between r and infinity, the electric field is going to be variant along this path between r and the radius of this sphere, which is r with uppercase, is going to be 0. Okay, as the electric field inside the shell is going to be 0. So in this path, the electric field is 0. But in this path, the electric field exists and it's measured by this equation. According to this, this integral must be splitted into two sub-integrals. One starts at r and at r lowercase and ends at capital R, and the electric field is equal to 0, so plug 0 directly. And regarding to the path is radial also. Anyway, this term equals 0 plus the electric field outside the sphere. We said is calculated by this equation. Okay, now as we see, this term is going to be cancelled out. We will end up with this term only. Now let's apply the integration, and we have applied it before. We applied an identical integration to this, and the answer was, and this is the potential inside the spherical shell. The distinct thing that you may notice about this equation, that all parameters inside it are constants. According to this, the potential inside the sphere is constant, and this seems logic when we try to prove the fact that inside the shell we have no electric field by applying the gradient operation upon the potential. And as we know, the gradient operation is nothing but the spatial derivatives, and the spatial and the derivative for some constant is equal to 0. So due to this, we don't have an electric field inside the shell, and according to this, we can build a new deduction that the absence of the electric field does not mean necessarily the absence of the potential. And that's the end of our video for today. See you.